Welcome to Lecture 22, entitled An Overview of the Divergence Theorem, Stokes Theorem, and the Fundamental Theorem of Line Integrals. So this basically lecture introduces these three major theorems, which more or less constitute the backbone of vector calculus. This material comes from Reading Assignment 4, the Introduction to Section 4, Part 4. And the objectives of this lecture just are to give you an overview of the theorems used in the remainder of this reading assignment and the geometric and mathematical relationships. No actual calculations, just to sort of wrap your mind around what these different types of mathematical relationships actually mean. And the main concepts and visualization skills developed within this lecture are the divergence theorem in 3D, and the equivalent theorem in 2D, which is called Green's flux theorem. Stokes theorem in 3D, and its equivalent form in 2D, which we call Green's circulation theorem in 2D. And lastly, the fundamental theorem of line integrals for irrotational fields, either in 2D and 3D, source-free fields in 2D, and source-free fields in 3D. Note, in this course we will not cover in any detail the fundamental theorem for integrals due to lack of time, and you are not responsible for this material. So more or less this is just to sort of give you a sort of a high-level overview before we start to dig into any details. One other matter of interest is that these notes basically start with 3D and basically evolve to 2D, whereas the textbook has taken the traditional view of doing everything in 2D, invoking 3D concepts in 2D, but not basically allowing a sort of a transparent understanding as to how you move from 2D to 3D. It's somewhat easier to go the other way around, which is effectively the route that I've taken in these notes and in the lectures. As usual, the second slide is just a summary of the slides to follow. Notice I've put one of the items in sort of an orange color. That's only to indicate that you're not responsible for the material, nor is it in the text or in the notes in any specific manner other than buried in an appendix. But I thought I'd put it here just to sort of to complete the notes. All right, so let's start with an overview of geometric conventions when applying the divergence theorem. And so there'll be a 3D version and a 2D version, the 2D version being Green's flux theorem, which we'll get into more detail a little bit later in the lecture. So for the divergence theorem, we are looking always at a closed surface. And so the picture on your right, just shows basically a sphere, but it doesn't have to be. It's a continuous smooth surface, so we can identify a vector normal to that surface. It's a differential area vector, NDS. And that encloses a volume. So a closed surface encloses a volume. And the convention here, when you apply the divergence theorem, will be make sure that the surface area vector is pointing outwards from a surface. Right? That's the only issue that you need to worry about, is that you apply the theorem correctly. In 2D, we're talking about a contour that encloses an area, closed contour. In this case, typically, we are always traversing the contour in a counterclockwise direction, which means the normal points outwards to your right. And so in this case, we're always concerned with a normal vector pointing outwards from the contour when applying the divergence theorem in 2D, which is more or less what we will call Green's flux theorem later. All right, so now let's consider an overview of geometric conventions when applying Stokes theorem. So, consider two cases, the 3D version of Stokes theorem and a 2D version. We'll talk about the 2D version with a specific name later in the course, but for the time being, it's useful just to sort of show diagrams and show the conventions in conjunction with these diagrams. So let's look at the 3D version of Stokes theorem, which is this one that you see here. Just a couple of points. First is that the orientation vector for a differential area on an open surface bounded by a closed contour point in a direction consistent with the right-hand rule. All right, so what does that mean? So here we have a contour. In this case, it's in a counterclockwise direction. And I've shown two surfaces bounded by the contour. One of these is this olive green planar surface in the form of a disk, and the other is this bluish surface, which is a hemisphere but it's bounded by essentially the same red line. So what we're doing basically with the right-hand rule is you point the fingers in the direction, the right-hand finger in the direction of the traversal. So that means you wrap your fingers in this direction, in the direction that the TDS is pointing, in which case the thumb is pointing in the vertical direction. And this will be the case for both this surface here as well as this surface here. This is actually the convention that needs to be applied, otherwise you're going to make a lot of mistakes. The direction for the orientation vector is consistent for all possible surfaces you can possibly create with a given contour. Example, the orientation vector of ds points upwards on both the hemisphere and the circle in the xy plane, and the red contour encloses both surfaces. So this is the general picture they say you need to look at in conjunction with the convention that's being applied. The thumb would point downwards for a clockwise traversal of the contour, whereas a counterclockwise traversal would result in thumb pointing outwards. So if this traversal would be opposite, that means we would just reverse the direction of this arrow. Your right fingers would point in this direction, and automatically your thumb would be pointing downwards in both cases. That would be pointing inwards from this semicircle surface in the case of a clockwise traversal of the contour. In a 2D case, basically, we only have an area which is in the plane. And here we're basically going to apply the same principle as we did for the 3D case, except that the thumb points in a direction which in 2D does not exist. The Z direction does not exist. However, there's a nice way around that problem, is that we define this to be an imaginary axis, and typically we give it a name of a pseudo-vector J. For scalars, we have J, which represents a scalar. Whereas for vectors, we have a pseudo-vector, which we call J. That basically allows us to define some form of axis of rotation, even though in 2 dimensions, Z does not exist. Either way, you can look at these 2 links if you want to look at these diagrams in more detail. So next thing to do is to consider the overview of the geometric conventions when applying the fundamental theorem for line integrals. As I stated at the beginning of this lecture, you're not responsible for the material, but by putting in here, I basically at least introduced you to the theorems that constitute vector calculus. So we're going to look at 2 specific cases here, the source-free field for the 2D case and the irrotational field for the 2D and 3D case. All right, and so what we're trying to do here is to try to see whether or not we can relate the endpoints on a particular contour to some specific scalar property. And the details will become apparent when we look at the actual mathematical relationships. So again, for the source-free field, the contour is traversed between 2 points, and that means that the direction normal to the contour for the 2D case must be taken to the right of the direction of traversal. And so in the picture that you see on the upper right, the direction of traversal is TDS, and to your right is NDS. And so you're going from the point at the top to the point at the bottom. In the irrotational field case, again, in this case, the contour is traversed between 2 points for the 2D and 3D cases. So just keep this in mind. The mathematics basically will come shortly, but really what we're trying to do is to identify whether or not integration along a contour can be related to the properties of the endpoints in all of the cases shown on this slide. All right, so now let's go into more detail and look at the mathematics, more or less the form. And then from there, in the subsequent lectures, we can actually use this information. All right, Stokes' theorem in 3D is stated in the top left-hand corner. It's bolded in orange. And so question is, what does this mean? Well, this means a closed contour integral. F is some vector field. This is a tangent vector, and you're integrating the dot product between these two around a closed loop. This, of course, is a circulation. All right, the net result is a circulation. What we're saying is that if you do this calculation, that's equivalent to taking the curl of this vector field and dot producting it with a surface area vector and integrating over the surface. And this surface basically is bound by this contour. And here, of course, the right-hand rule would apply. So, for instance, the direction of t and the direction of ns are linked to each other through the right-hand rule. And so if we use this picture again, here's TDS, and going the right-hand rule, the area vector will be pointing upwards. And again, because you can choose an infinite number of surfaces bound by this contour, the actual choice of surface becomes a degree of freedom. And so, for instance, this is one possible surface bound by the contour, this is another, and the area vector, again, according to the right-hand rule, would be pointing outwards. All right, so more or less, this is the picture, and this is the description to go with it. All right, what about the divergence theorem in 3D? All right, in this case, basically, we have this relationship, which essentially says that if you take a vector field and dot product with a differential surface area and integrate the resultant scalar value over the closed surface, this means closed surface, that's equivalent to taking the divergence of the vector field, integrating it over the volume enclosed by the closed surface, and that result should be identical to this on the left-hand side. All right, and so from a diagram point of view, since we're using the divergence theorem, the surface area vector must be pointing outwards from the surface that's bounding the interior volume. And so this is always something you should keep in mind so that you do not confuse the Stokes theorem convention with the divergence theorem convention. So that more or less gives you sort of an idea of what the divergence theorem is all about. All right, let's look at then what happens when we move into 2D, and that would be Stokes' theorem applied in the 2D setting, and we'll call that Green's circulation theorem. We will prove this a little bit later, but for now, basically take the formulas as a given. So let's look here at the 2D equivalent form. So this would be a vector field in 2D, and so this is the way you would describe it in terms of a x component as a function xy, y component as a function xy. And t of 2D is equivalent to t. Basically, we're just going to interchange these two. It's understood that the tangent vector here is going to be a 2D vector. If we were to take the dot product of the field vector in 2D and the tangent vector, which is the resultant is a scalar, and integrate the resultant scalar function around the closed contour, that's equivalent to taking this expression here. In other words, taking g partial x minus f partial y. This is a scalar function, integrating over the area enclosed by the contour. These two are equivalent. Again, the convention is the same. Basically, you're going counterclockwise around the circle. This is called Green's circulation theorem, or equivalently, it's Stokes' theorem in 2D. All right, so let's look at the Green's theorem. Let's look at the divergence theorem, but in a 2D setting, in which we call it Green's flux theorem. So in this case, basically, we're dealing with the vector field in 2D. Again, it has a similar relationship as the case for Green's circulation theorem. But in this case, we're taking the normal to the contour. And again, the normal to contour is to your right, assuming that you're traversing the contour in a counterclockwise direction. If you take the dot product between these two, you get a scalar function. And if you integrate that scalar function around the closed loop, again, this now will become a flux. All right, this has units of a flux. That's equivalent to taking this entity here, where you're taking the partial of f with respect to x, adding it to the partial of g with respect to y. This is a scalar function, and integrating over the area enclosed by the contour. All right. So this is more or less called Green's flux theorem. And again, in the flux theorem, the arrow is pointing outwards from the contour. All right, so this is more or less the mathematical form of Green's flux theorem. I think if you understand these conventions and what's being done, the actual numerical calculations are things you've already done, because in one case we're dealing with contour integrals, and the other case we're dealing with surface integrals. All right, so now this portion of the lecture is for your interest only. We're not going to be looking at detail again because we just don't have the time, but I introduce you to it anyway. It's called the fundamental theorem of line integrals. There's one for irrotational fields, and there is also one for source-free fields. So we'll do each one in turn. For irrotational fields, we have basically this expression. So this essentially says f flux dot TDS. So this would be an irrotational field. F equals F flux would be an irrotational field. And this is equivalent to integrating between some point A and some point B. All right, this is basically how the theorem is set up. And if you define F flux to be the gradient of a scalar function, all right, so this is the definition, F flux is grad phi, then this integral is more or less equivalent to evaluating what this scalar function is at point B and subtracting it from the value of the scalar function at point A. So this is the fundamental theorem of line integrals for irrotational fields. And so the other thing that's interesting is that it doesn't really matter the path that you take. So this path that you take from point A to B, it could have gone this way, it could have squiggled around and come this way, but the net result is the same, that independent of the path taken, you always end up with a difference between the value of this scalar potential evaluated at point B minus the value scalar potential evaluated at point A. All right, and so these are, as we said earlier, these are conservative fields. When you have something of this nature, right, then this is a conservative field. All right, for a source tree field, I mean, the problem looks more or less the same, except instead of doing an integral with respect to a tangent vector, it's with a normal vector. So in this case, this is, if it's source tree, then it means that we only have a circulation field, fcircle.nds. And again, we're going to integrate between 2 points A and B. And in this case, it's related to another type of function, not the scalar function phi, but psi function, evaluated B minus the value of this psi evaluated A. So the value of psi evaluated here minus the value of psi evaluated here. Now this psi, which is different than what we saw earlier, is a function of x and y because it's a two-dimensional problem. We call this a stream function to distinguish it from a scalar potential function. So this is a scalar stream function. And if you set things up in such a way that you take the derivative of the stream function with respect to y, and that becomes your x component, and then take the derivative, this partial derivative of the stream function with respect to x, make it negative, and make this the y component, and then state that this is equal to f circulation, then effectively this expression is true. Okay, so this is just a note that a 2D stream function is a scalar function from which the circulation field is constructed. The components of this field are such that if you take the divergence of the circulation field equals 0. Now you can prove that for yourself, because the divergence would be taking this derivative with respect to x and then adding it to the derivative of this with respect to y. But these functions are considered continuous, and so whether you do dy dx or dx dy, essentially you're dealing with the same outcome. The only difference is when you add them, you're actually subtracting them, which means the net result is 0, so that's consistent with this expression. So we know that this is the correct expression to work with. Again, the result is path independent. In other words, if I go this route or this route, this result doesn't change. It's still going to be the difference between the value of the stream function evaluated at B minus the value of the stream function evaluated at A. All right, so this is another one now which deals with source tree in 3D, where we're dealing with surfaces. And so here what I've done is written it out. It's not in the notes. It's sort of buried in one of the appendices. But all I'm doing now is I'm using the same formalism. Instead of using a contour now, we're using a surface. And so what I'm basically saying, if I take an open surface, fcirc.n/ds, then because we know that this is going to be a source free field, that means I can write this out field in terms of a curl of a vector potential A. And then I can use Stokes' theorem to relate this expression to this expression. So if I take an open surface, the curl of a vector field .nds, that's equivalent to taking a closed loop contour A.ts. And so this is more or less the picture. This again, the Stokes theorem picture. And again, it doesn't really matter whether or not you deal with this surface, which is bounded by the contour, or this surface. Effectively, it's independent of the surface as long as basically this contour is bounding that surface. Okay, so this is just a summary. The other thing I just want to make note of here is that this vector potential A, which up to now basically is just some entity which you haven't even seen before, will be investigated in more detail in the EC221, the electromagnetics course, next semester. Okay, so the last thing I want to do is to summarize some of the key definitions. All right, so let's go through these in turn. First is that a vector field is comprised of a component F flux, which is irrotational, and a component F circ, which is source free. And just again, this is just a question of convention of names. A vector field which is rotation free, also called irrotational, is also defined as a conservative field. It's just a label that's attached to an irrotational field. Secondly, a vector field which is source-free is defined as a source-free or solenoidal field. Again, this is basically conventional terminology has been used in the past. A source-free field, that is F is equal to F circ, is defined by the vector equation F equals the curl of some vector potential A. And A, what does A look like? Well, A has an X, Y, and Z component if we're basically talking about a 3D problem. On the other hand, if we're dealing with a 2D problem, then what we do is we assign a fictitious Z component to the vector potential. And so you have 0, 0, A of Z. But the vector potential A of Z component can only be a function of X and Y, since we basically define this as being a 2D problem. All right, so we've done this again because if we're going to take the curl of a vector field, we need to have a three-dimensional vector field. Okay, so third bullet point is if an irrotational field, that is F is equal to F flux, is defined by the vector equation gradient of scalar potential phi. So scalar potential phi in 3D will have 3 components, and scalar potential in 2D will have 2 components. And so the last thing to do is to summarize all the different cases that we considered. If we have a conservative field, right, a conservative field is irrotational, either for the 2D and 3D case, then we have these 2 expressions. We essentially say if we integrate f dot ts ds between a point A and B, so it's like a partial circulation, and then go from B back to A, which means we formed a closed loop, then the result of this calculation is going to be equal to 0. In a more succinct fashion, it means if I take any closed loop, which means I'm taking circulation, is equal to 0 if I'm dealing with a conservative field or an irrotational field. If it's a source-free field in 2D, then effectively instead of using TDS, I'm using NSDS. Again, what I'm doing is going from A to B and then from B to A. If I do this integration around a closed loop, I end up with a value which is equal to 0. Or, effectively, because it's a closed loop, I can take this and simplify it and just write as a closed loop integral, f dot NSDS equals 0. This is the case for a source-free field in 2D. For a source-free field in 3D, we start with the notion of a closed surface. So this means F, the vector field F dot NSDS. This is the surface area vector pointing outwards from the surface. And now what we're going to do is break this up to an upper surface and a lower surface. These 2 surfaces are glued together, but they share a common boundary or contour, at which point the 2 surfaces are stuck together. All right, so we just broke them out in this fashion. Now, because this is a source-free field, then we can make use of the fact that F is the curl of the vector potential A. And so we just substitute in here the curl of A, and we substitute in here the curl of A. But by Stokes' theorem, this expression is equivalent to a closed contour integral over the vector, the tangent vector around the closed contour, which is bounding both surface S1 and surface S2. And in this case, curl of this becomes also curl of A, but the contour now has to be different because this surface is below the contour, whereas this surface was above the contour. And so to be consistent with Stokes' theorem, this contour, you have to go in the opposite direction. That's why there's a minus sign shown here. So that means that this term and this term are equivalent except they're opposite in sign, which means if I add them together, I get 0. So the ultimate end point, or end statement would be that this integral over closed surface is equal to 0. So that concludes lecture 22. Thank you for listening.